right, so give me a second, let me to adjust the camera. Zoom in. Okay. I think I'm very successful to get you confused last time. Thank you so much. So you stole another one from your boss?
No, so the same one.
Oh, the same
Our
one.
lab used the exact same model.
Okay.
What, which one? Nordic.
It's rich.
Everyone says it's rich, I don't know why.
Huh?
I don't know why everyone says it's rich.
Oh, there's some reason we can talk after.
Probably something I don't want to know.
Okay, so we give two examples to calculate the entropy change last time, right? So the key idea is, again, we do not know what entropy is, and we even do not know what's the definition of the entropy. But from our study, from the Canal cycle and other example, we can find one parameter linked to the entropy, right? So if the process is a reversible process, we know that we can calculate the change of entropy by this equation, right? Once again, emphasize one more time, this is not definition of entropy, this is just one calculation method. But anyway, entropy is a thermodynamic parameter, only depend on the states, the final and the initial state. So, in other words, in order to calculate the change of entropy, it's not necessary for us to know the specific or detailed process, right? What we need to know is just the final and the initial state, right? But in order to calculate the entropy change in an irreversible process, for example, mix the hot and cold water, the free expansion, we do not know the detail of the path. But on the other hand, we can artificially create a pathway to link this to this and then calculate the change of entropy. Right? This is what I told last time. Mixing the water. Although we know that the mixing to water and water reaching the equilibrium, temperature is not a reversible process. But we still can calculate that change, right? By creating two independent reversible processes. By cool down one water and warm up the other water and then put them together. Okay? There's something I have not explained yet. You know that we mix the water, they reach the equilibrium temperature, right? And for the reversible process, to mimic the process, we cool down one cup of water and warm up the other cup of water, right? To reach the thermal equilibrium. That means the same temperature. We still need to mix them. Correct, everybody? Will that kind of mixture change the entropy? Everybody shake the hand. No, it doesn't change, right? So we have one water, the other cup of water, they have exactly the same temperature, pressure, whatever, mix them together. The entropy, it not change, the entropy changes, right? It's just double, right? You know what I'm saying? You have 2 cups of water, you just sum their entropy. But why is that? Okay, so this question has not been answered yet, right? Just keep in mind we have this question, okay? But I'm not going to talk about it right now, okay? Let's go back to calculate the entropy. Let me ask you a question, okay? Probably online students have no way to answer my question right now, but if you have a couple of minutes, you can just talk to the camera. Hopefully I can still hear something from the speaker, but probably not. So the question is, do you want to have one more math practice to show you how to calculate the entropy, or we move on to the next chapter?
More practice.
No practice? Okay, I give you another practice, okay? But I will announce the homework. Okay, I will announce homework this week, so you have 1 week to finish the homework. And afterward, I will spend 1 class just to answer the questions in the homework. You know what I'm saying? I don't want to just give the homework and you right or wrong and give a grade. Doesn't work, okay? I give you feedback. I spend probably 1 class to solve the equation, each one for you guys, okay?
Have
So
you published the homework yet, or are you still going to?
I'm going to.
Okay.
I'm going to. I'm still not very familiar with the online system yet, but anyway, so if that work, we just follow the very traditional way. Papers, you give me the hard copy. Everybody online send me the email. The only thing matter to me is your feedback. Okay, I don't care about whether it's the online or in class. How you give me the homework, it doesn't matter. As long as I know that you understand the knowledge, I'm okay with it. Understand that? So I don't worry too much about that. I need to establish a kind of like a question on or assignment on the canvas of that. It's just a waste of time. Anyway, so I will go to modify the video, so I cut this kind of speech so that the dean and the department chair will not see what I'm saying in class. Okay, so this is the example on the textbook. Okay, if you have textbook, you can read it. But I'm going to talk about it. Okay, I think it's better for me to mention it again. This practice is more quantitative. Okay, you can call it the practice 3. All right, the question is like this. So I just copy what's on the textbook, okay? We have 5. We have 5 more of monatomic. I have no idea how to pronounce it. Monotonic ideal gas. Okay. Contained adiabatically at 5 atmosphere pressure and 300 K. Then the pressure is suddenly released to 10 atm. And the gas undergoes and the reversible expansion. During which it performs 4,000 joule of work. Okay? Do you understand the process? We have 5 moles of the, how to pronounce it? Monotonic? Monotonic. Do you know what the monotonic means? That each molecule has only one
inert gas.
Only one atoms. Okay, inert gas. So then helium, neon. This is the monotonic ideal gas. Okay, I contain What is adiabatic meaning? What is the adiabatically mean? There's no external exchange, right? At 550 ATM, ATM is not where you got the money from, okay? It's an atmosphere pressure, okay? And 300K, 300. I would like to say that I got the 300K from one ATM. Okay. Then the pressure is suddenly released to 10 ATM, okay? Atmosphere, and the gas undergo an irreversible expansion, and during which is performed 4,000 joules of work. So that's all the information we have, okay? But what we know is, first of all, there's no thermal exchange with the environment, right? The other thing is this irreversible expansion, but different from the example we show in the practice one. It's not free expansion, right? It's not free expansion because it's also output 4,000 joules of work. Correct, everybody? So the process is so complicated, right? Anyway, so then the question one, okay? The question one, show the final temperature. Show the final temperature. I give you about, give me a second. I cannot see the time. Why that the one is not on? So I need to know the time, otherwise I cannot control the class. Anyway, I give you about 5 minutes to consider this problem, okay? To calculate the final temperature. Once again, this is an adiabatic process, so we cannot calculate the change of temperature by calculating the delta Q, okay? It's not free expansion either, okay? It's not free expansion either. And it's not it's not adiabatic expansion. So PV to the order of gamma is constant, that doesn't work. And it's not the free expansion, okay? Free expansion, then the temperature doesn't change, right? It gives work. So that means it's not free expansion, it's not adiabatic expansion. So you need to consider how to calculate. What's the question?
Is it first go to 10 atmosphere of pressure and then does
No, simultaneously.
Oh.
When you suddenly release to 10 atmosphere, it gives work.
So when it gives the work, it's always at 10 atmosphere.
No. It suddenly released to 10 a.m. and undergo an irreversible expansion. And during the expansion, it's performed work. It happens simultaneously. Okay, so let me think about the car engine. Your car engine, you have the chamber, right? Understand what I'm saying? Then the gasoline and the air mixture suddenly got exploded, right? You have high pressure and push the piston to make your car driving, and then the pressure going down, right? It's going down. That is the process. Okay. So you can say that is basically it's adiabatic, and it's not free expansion because it keeps working. Okay. Basically, this is the process for the car cylinder work. But anyway, that's all the information you have. And of course, ideal gas. We're going to have a discussion at 12:15. Okay, we have 2 minutes. I find my handwriting is really terrible on the web. The line not straight up and down. Anyway, so if you have difficult to read my writing, let me know, okay? I think in the classroom still fine, but in my student, if I have any complaint about my handwriting, let me know, drop me a message, okay? I'm trying my best to improve it. May I erase this part?
Yeah.
What do we know? We know first law, second law. And regarding this system, what about delta Q? Zero, right? As long as you see something like thermal isolated or adiabatic, delta Q equals 0. What about first law? du equals to what? And
Delta W.
correct? Delta Q equals 0. Delta W equals what?
Negative.
No, number.
Negative 4,000.
Negative 4,000. Correct? Then what about change in the total internal energy? What's the change of internal energy?
It's negative work.
Yeah. We do not use the. It's not a good expression anyway. So the. This is the derivative. I mean the form. Okay. Now that's better. That's more mathematically precise. That's what we know. Correct, everybody? Right? What about the internal energy of the ideal gas? Still remember? What's the huh?
And 3 over 2 N R T.
What?
3 over 2 N R T.
Correct? That's the internal energy of the ideal gas when we have N. Is that right? We already proved that last week or 2 weeks ago. Correct, everybody? And the internal energy of the ideal gas is only a function of temperature. Right? It's only the only function of the temperature. We have this equation. Then the initial temperature is what? 300 K? Correct? And we have the final temperature. CV, what about CV? 0 or 2 as she mentioned, right? R times N times dt. Correct? And this one equals to what? 2, 3, N is 5. R is what? 8.31, right? Times T final minus 300K equals to negative 4,000. Is that correct, everybody? And then do some simple calculation. You will have the final temperature 236 Kelvin. That's simple. Okay. Questions? Comments? Okay. Second question. Calculate the entropy change. Before we do that one, let me do some analysis for you guys. Okay? Once again, entropy is a what? Is a thermodynamic parameter, right? It depends on what? State. Does it depend on the specific root? No. Okay, keep in mind. Okay, so we know the gas. This is P, this is V. At the beginning, we know the gas is at what? 50 atmosphere, right? And 300 K. And the final is what? Is 10 atm, right? And what's the temperature again?
236.
236. Okay. I did not calculate, okay? Just the calculate. It's very simple calculation. You can do your job by yourself. We know these 2 points. Correct? We know these 2 points. We need to find a way to link these 2 processes. Right? We need to find a way to link these 2 processes. Correct, everybody? And how many different types of the reversible process we already learned from the class? 4. Which 4?
Iso or isobar,
Iso what?
isotherm.
Isothermal, yeah. Isothermal. Isothermal is what? What is isothermal again? Same temperature, right? So for that one, the isothermal curve looks like this, right? And for that one, the isothermal curve also looks like this, right? Let's make the point a little larger. So they don't have the, they do not cross each other, correct? Because in different temperature, right? So we have 2 isothermal process. Can you build up the, can you link this 2 point with a single isothermal process? No, right? Okay. What about other process? Reversible process? What do you guys we already learned? Huh? Adiabatic, right? Adiabatic process. So what the adiabatic process looks like on this curve, on this chart? It's still a curve, right? So the curve given by this equation. Correct, everybody? So the key point of the adiabatic is like this, right? So what's the adiabatic curve looks like? Need not. Sorry, so it's not the, it's adiabatic, yeah, it's adiabatic, okay, that's fine. Adiabatic expansion or whatever. Yeah, so what's the adiabatic? Adiabatic is not a very strict terminology. We should call it reversible adiabatic, okay? Because that process is also adiabatic. Adiabatic only tells you delta Q is equals 0, right? We need to very specific. This is a reversible adiabatic, okay? Reversible. And the reversible adiabatic has this equation. So what's the curve looks like?
It will cross the 2 of them.
Does this go link these 2 curves?
Yes.
Are you sure?
Yes.
We are talking about this is reversible adiabatic. And that one is what? I already mentioned that's the irreversible adiabatic, okay? Okay, anyway. So let's do some calculation first, okay? To see if through an adiabatic process, we expand the gas from 50 atmosphere to 10 atmosphere, what's the final state, okay? First of all, let's calculate, do some calculation, okay? If the process is, if not, if the expansion is reversible adiabatic Okay? What is the final temperature? Okay, let's do some calculation, okay? The expansion of what? Expansion from 50 to 10 atm, okay? Let's do some calculation first to see how it works, okay? To see whether we can, the purpose is to see whether we can link these 2 points through a reversible adiabatic process. We should know it's not, okay? Because in the question, I already told you it's inward reversible. But anyway, let's do some calculation first. So for the reversible adiabatic process, we already know the PV gamma equals to a constant. Correct, everybody? And the same thing. So for the ideal gas, we know that the PV equals to nRT, right? Let me see. Yeah. Let's make the job easier. Let's make the job easier. Okay, yeah. So at the beginning, then we have what? We have a 50 atmosphere times V initial gamma equals to 10 atmosphere times V final gamma. Correct? We have this equation. Right, everybody? Initial state 50 atmosphere, final state 10. Atmosphere, V final. Then from that one we will have V initial divided by V final to the order of gamma equals to 1/5. Correct? So what's the value of gamma? And from that one, no, it's fine. What's the value of gamma? Gamma, definition of gamma is Cp divided by Cv, right? For the ideal gas, Cp is 5/2 R, right? And Cv is 3/2 R, right? Then the gamma equals to 5/3. Correct? So we put that one in the equation. What we have is, we will have V initial minus V final equals to this kind of expression. Correct? A little bit weird. Is that right?
And gamma, when you say Cp over Cv, Cp and Cv are of the air
Yeah, Cp is the constant pressure heat capacity
for air.
and for air.
Okay.
And V is the constant volume. Then we will know that the T initial minus T final should equals to what? Should be P initial V initial divided by P final V final. Correct, everybody? And then what about P initial? It's 50. P final is 10, right? Then the ratio is 5:1, correct? And V initial minus divided by V final is this value. Correct? Right? So what's that? This one equals to 5 to the order of 2/5. Right? That's the ratio. You just do some calculation. Then the final temperature is what? Final temperature equals to T initial divided by 5 to the order of 2 over 5. And this one equals to 100. Okay, so do you think this temperature and that temperature is the same? They're not the same, okay? So that means if from the starting point, you go through an reversible adiabatic process, the curve looks like this. You have even, if you go to the something, give me a second. Yes, the pressure. This is, if you go to the 10, you end up with this point, correct? The same pressure, volume is smaller, temperature is smaller, right? What's the question?
Where did the Ti over Tf equals PIVI over PFVF come from?
The PV equals to nRT, right? Initial. Then you have the P initial, V initial equals to nRT initial. P final, V final equals to nR.
Just
P
use the
final.
ratio out of it, the rest
Right.
cancel.
That's it. Because we do not change the number of atoms. And then now, if through the adiabatic process, we end up with this point, correct? And the temperature here is 157.6 Kelvin, right? So that means what? That means we still cannot link these 2 points through an reversible adiabatic process, right? They cannot be linked by, with the isothermal process, they cannot be linked by an adiabatic, reversible adiabatic process. Other reversible process we have already learned? We already know? No.
So bar.
Huh? Any other processes? Reversible in your mind?
Isobaric,
Huh?
constant pressure,
Constant pressure. Something else?
constant volume.
Constant volume, right? What about constant pressure process? Right? Constant volume. Something like this, right? Okay. So since we already know that, we already make the calculation of the adiabatic, reversible adiabatic process here, right? And then we can link this point through a what? Through a constant pressure. Constant pressure process. Okay, that means we cannot link these 2 points through a single step. We have to have 2 steps, okay? The first one is adiabatic, reversible adiabatic process, and then a constant pressure process, and reach this point, okay? We can do the calculation of the entropy. Again, this one is what? What's the name of this process?
Constant pressure, isobaric,
Adiabatic. Adiabatic, right? We find the reversible adiabatic process.
isotropic,
Isotropic, what is isotropic?
constant entropy, because if it's adiabatic and reversible, then
Oh, I don't know that. Adiabatic, okay. Yeah, adiabatic. We insist to call it adiabatic. Anyway, so what the information we learn from it? If we call it adiabatic again, right? And in the reversible process, for sure, right? Right? Correct, everybody? Because the delta Q is 0, and it's a reversible process, then the ds equals to delta Q divided by T. We know this is 0, even we do the integration, the final delta is also equal to 0. So this part doesn't change the entropy. So in order to calculate the entropy change, we only need to calculate this part. Correct? We only need to calculate the entropy change during the constant pressure process. Right, everybody?
Is it all the same if you start from the isothermal where it was ND too high and then do an iso?
You can.
You can.
You can.
Okay.
You can. You can do any kind of.
Okay.
Let me tell you what's the reason for that. Okay. After we finish the job, I will answer his question. Okay, answer his question. What we can do now out of this. So for that process, we follow the same definition. Okay, delta Q divided by T. So we know that this process is iso is not. You just make me confused. Constant pressure process. Okay. The reason is that because textbook always getting constant pressure, constant volume, but these use isothermal. You know what I'm saying? So we do not change the terminology. Anyway. So what about the delta Q in the constant pressure process? What is the delta Q in a constant pressure process? The temperature change, right? For the constant pressure process, the temperature change. If you compress gas or release gas, the temperature changes. Correct, everybody? Still remember we talked about something we call is the enthalpy. Remember? We talked something about entropy. During talking about entropy, we introduced another concept we call is the constant pressure thermal capacity, heat capacity. Correct, everybody? What's the definition of the constant pressure thermal heat capacity? Something like this, right? Delta Q equals to Cp dt for constant pressure process. Correct, everybody? Is that true?
Are we really just supposed to know that?
Of course. I already mentioned that weeks ago. Okay. Although I don't want to give you the homework, you still need to review what we're Anyway, so we know that, right? So then we put this one back to that equation. We have this relationship, right? Then delta S equals to integration from this point to this point, right? 157.6 to 236 Kelvin Cp T. Okay? This one, we already know the Cp, right? It's the 5/2R times N, right? And it's 5 more. And then ln T. The upper limit is 236 Kelvin. The bottom limit is 176. Okay? We're going to do the calculation. Then this one equals to 5nR ln 26157.6. Okay, you can do the calculation. Okay, it's just a numerical calculation, so it's not necessarily a problem. Okay, so back to the question. I forgot which one asked me. So is that possible for us to link these two points with other processes? Yes, you can. Yes, you can. You can do a constant process at the beginning, and then use another reversible adiabatic process to link them. No problem. You can also add something like this. First of all, you go to a constant volume process and reach this point, and use this kind of like the isothermal process. Go here. It doesn't matter. Okay? They always give you the same result. What's the reason for that? We already improved that during we talked about the canal theorem, canal circuit. I mean, like the canal circle. Okay, as long as you form this loop, the integration of the ds always equal to 0, right? That means if you go from this point to this point to this point, and go back, you form a circle, and the change of the entropy always the same. Okay, so no matter what kind of crazy processes you calculate, it always gives you the same result. But you choose the simplest one. Anyway, so if you don't understand what I'm talking about or you still have difficulties, fine, I'm going to give you a hard time during this week. You have a full week to think about this process, okay? I give you homework. And we still have a chance to talk about it. And you also have your midterm.
What is that?
Huh?
You got a date for that?
What's that?
Is that the syllabus, sorry? The
I'm
date
not
for
saying
the
that
midterm?
we have the midterm next week.
Yeah.
But I'm saying the question will appear in the midterm.
Okay.
So if you still cannot solve it, I'm going to repeat it again. But don't worry. So if nobody can solve the problem in midterm, it's my fault. You know what I'm saying? But if only one person cannot solve it, it's not my mistake. But if nobody knows how to solve the problem, it's my mistake. Either the question is so complicated, or I did not cover the key point in my class. So in that case, I'm going to repeat again to make sure that I understand what I'm talking about. All right. We give you three practices, right? But anyway, so we can bring as many questions as possible on this topic. You have the whole semester to practice. Shall we move on to the next chapter? Still entropy. What's going on with this guy? The reason I'm talking about, as I mentioned, most of the question you have right now is that you do not know what entropy is at all, right? We only know the expression. And in the textbook, they call it classic thermodynamics. They only tell you there's a quantity we call it entropy, and for the reversible process, the entropy change is larger than 1 or larger than the dq divided by d. For the reversible process, they're equal to each other. Okay? But what is the entropy? And then, if that is the irreversible process, if you want to calculate the entropy change in the irreversible process, you need to find an alternative reversible process to link these 2 points and calculate the entropy. And eventually, we will find delta S always larger than dq divided by t. That's what the classical thermodynamics tells us. That's it, right? But nobody can tell us what the entropy is. What the hell it is? Okay, it's so mysterious, floating in the air. Nobody knows, right? We just.
I was just about to ask if it has units.
What's that?
I was just about to ask if it has units.
It has unit for sure. The reason is from this equation you can see ds equals to what? Delta q divided by t, right? What's the unit of q? What about the t? That's the unit of the entropy, joule per Kelvin. Thank you so much. You make us know more information about it. At least we also know the unit. But nothing
Still know what it
else.
is though.
Huh?
Still know what it is though.
Yeah, we don't know that it is. I mean, who asked me last time at the end of class, how do you know all this stuff? Oh, it takes years. Definitely not one semester. I mean, I guarantee no matter how hard I try my best to convey my idea to you, you still don't understand all details about thermodynamics until you really use it. You know what I'm saying? And the first time I was in roughly the same age when I learned thermodynamics. That means when I early 20, even younger, probably around 20. Right now I'm 40, more than 40. 20 years. So don't be worried. If you don't understand, don't be worried. But you can worry about it. You were fine when I midterm. But I guarantee that it's not so crazy, okay? The reason that we are not working on like competition. I just want to make sure you understand the fundamental principles. And the key ideas, okay? The key ideas. I mean, the most fundamental part. You don't want to make a fundamental mistake. But unfortunately, even the big guy in the top of the field, very famous theoretical physicists, still make mistakes when they go to the thermodynamics. Let me tell you, when I was at UCLA doing my postdoc, my supervisor published one paper in Nature, and everybody was really happy about it. And then there's a review, and then a few months later, there's another scientist wrote him a message. He said, I don't think your mechanism explained in the paper are correct. I have an alternative, trivial explanation. So this is not something new, but very trivial. No, impossible. We already built the model, and the model, can explain the theoretical explanation. And then they go back and forth several times. And the editor said, okay, it seems like both of you have different kind of opinion, different explanation. That's fine. I mean, when we do research, we always have this thing. And then that guy still insists there's something wrong with it. And then eventually, the editor agreed there's something wrong. Do you know how he proved that there's something wrong with it? Okay, it's proving that way. Let us assume your equation is correct. This is the energy you need to input to the system to see the phenomenon. This is the energy delivered by the phenomenon. You can find that you input less energy than output. Where does the energy come from? You disobey a very fundamental law of thermodynamics. So definitely wrong. Okay? Yeah, it's wrong. And then nature withdraw that paper. You know that? That is the golden rule. So it's wrong. I mean, it happens. Because when you do the research, you're always struggling with kind of a very detailed mechanisms, right? But you forget a very fundamental law, conservation of energy. And entropy cannot spontaneously become smaller, right? There's another statement. That guy already passed away, unfortunately. Very big theoretical guy working in the quantum materials, like the topological insulator. That guy working in Stanford, you can check online. Who is it? And then I was working in the same larger team. And one time he gave a speech. Okay, since we talk, we know the topological insulator. Okay? So we have topological insulator. And then the electrons have the spin up, can propagate along this edge with no energy dissipation, go from one edge to the other edge. And on the bottom edge, the same thing. The spin down electron can move from this side to this side without any kind of scattering or without losing any energy. That's correct. That's fine. So the electron can pass through this end to this end without losing any energy. That's fine. And then he said, with this kind of technique, in the future computer, we link the CPU and the memory with this kind of materials. Then we do not need to consume energy to deliver the information from one part to the other part. Then here comes the issue. Okay? What's the issue of it? And nobody realized there's an issue, and eventually we find out it's not right. When we give the speech, nobody realized there's an issue. But eventually somebody told me that that's not correct. We don't want to give you embarrassing in front of everybody, but it's wrong. What's the reason for that? The reason is information is what? Have you ever learned some information theory before? Information is entropy, right? Think about it. If you only have a piece of the blank hard drive, there's no information there, right? Everything is just ordered randomly. Then the entropy is very large. So if you put information in, you are removing the disorder. You make something ordered, 0, 1, 1, 0. Basically, information is ordered, right? If you want to increase the order, you have to lower the entropy. You have to consume energy. Otherwise, the process doesn't happen spontaneously. So I don't care about any kind of detailed mechanism. So this statement disobeys the second thermodynamic law. No matter how beautiful the picture looks like. It's totally wrong. It's totally wrong. Okay? The other example I told you, you can check online. It's a very hot topic a few years ago, but I still have a question. I cannot be 100% sure, but you can have your own judgment. Check the Nature of Science paper, probably 5 years or even, not 5, probably 10 years, 7 years ago. They call it there's some scientists in the University of Colorado Boulder. They claim that they develop a kind of film can help, can increase or accelerate the radiation, the cooling process, mediated by radiation. For example, you have some hot object, right? This one you have some really hot object. It can naturally cool down through radiation, right? It's just give the thermal radiation. That's the reason we'll stand very hot body, you will feel the heat, right? That's through the radiation. So probably in the infrared range or even visible light range, if you become very hot, you give the visible light. So this is radiation, okay? Through the radiation, you release the energy to the environment, correct? This is spontaneous process. And they claim we can add another type of film to cover it, okay? To cover it. And then this field matches the atmosphere, infrared, window, whatever. So it's going to help this kind of radiation happens even faster and directly deliver this kind of radiation across the atmosphere of the Earth to the universe. It makes it cool down faster. On the other hand, it blocks all other radiation from the sun. So that means with this film, the inner part will become cooler than the outside, spontaneously. Okay? So think about whether you're right or not. Okay? But from the data, you'll find the temperature here and here are always the same.
Their assumption was it would be cooler inside than it would be outside?
Yeah. The assumption is like this. So if you put the object in atmosphere, it's hotter than if you put the object inside their film. I mean, my argument is, okay, of course, you even do not need to make any film, radioactive film, assisted film, no, don't worry. You just put in the shade. It's definitely colder than what else. But anyway, so I know the guy, I personally know him. Him trying to find the investment to the United States, but no, not a single cent. Because you know that sometimes when we do the fundamental research, we make some mistakes. But when you go to company, these guys are super smart. They do not want to waste the money. Your mistake is probably just one paper. Their mistake is millions of dollars. Okay, anyway, so the reason I told quite a lot of funny stories is because, keep in mind, the most important thing so far you want to know, even if you can make the mistake during the calculation, even if you sometimes you forget to use the constant pressure thermal capacity for this kind of the constant pressure process. That's totally okay. Okay, after several practice, you will learn this process. But one thing keep in mind, you don't need any practice. Just, pin this idea to your brain, the first law and second law of thermodynamics. Okay, that's the most important thing so far you need to remember. But the next job for us is giving an explanation of what in hell the entropy is. Okay? So in order to understand what the entropy is, we need to go to the next topic. It's called, how much time now? Well, that's the next time. You can see that I spent a lot of time. I think we have one class delay, because according to the syllabus, the schedule of syllabus, we should already start a discussion on the statistics part. But anyway, I don't mind that too much, as long as I can make you understand. Statistics thermodynamics. So on the textbook, it's a very short chapter. Okay, it's only talk about the statistic explanation of entropy. Okay, that's true. The one main purpose of the statistic or the motivation to establish the statistics thermodynamics to explain what entropy is. Okay, but eventually we will find that we have more information than that. Okay, we have more information than that, and you will find that the textbook, the chapter, some part is not complete, even wrong. Okay, follow what I'm saying. Okay, I can guarantee it's more correct than the textbook, but not necessarily 100% correct. Okay, so from the class we talked so far, what we only know is that ds larger or equals to the dq by the t. Right? We don't know what the ds is. But I think most of you, and we also mentioned at the beginning, remember, we are talking about what is spontaneous process. I mentioned that if you only have one body, two bodies, spontaneous means the driving factor to make the spontaneous process happen is only energy, right? And then I told you some of these things about the parking garage, right? So whether you always want to park your car on the first floor, if there's only one single spot, you don't want to waste your time to look for a single spot, or you want to go to the second floor, right? Then we know that the driving factor for this kind of statistic or manifold system, not only the energy but also the statistic behavior, right? But yeah, I think somebody of you also asked me a question. What's the statistic you are mentioning about? We don't know. I just mentioned there's some statistic behavior, right? What does that mean? Okay, so to answer your question, right now we're going to start answering the question. Okay? So, first of all, we need to understand two concepts. I already mentioned that, right? So one is the micro state. Okay, that is state we can measure, we can feel with our naked eye, with our hand, with a ruler or whatever, right? And then all the parameters. So what's the parameter we have? The microstate parameter. So what do we have? Can we name some?
Sure.
Temperature, pressure, volume. Yeah, entropy, that's fine. Although we don't know how to measure it yet. Entropy, Q, right? Something else?
H.
Enthalpy, that's fine. And something. We have a lot. But we know temperature, we know pressure, we know volume. The Q, kind of entropy are so mysterious. Nobody knows. Okay, so then, but we know that all this kind of factor, actually you have gas. But only think about gas. The gas is composed of what? Molecules, right? There are so many molecules. Okay, so even think I have a tank of gas, and you have a tank of gas. Hydrogen, the same thing. We purchase from the same company. Do you think they have exactly the same MI chrome state? Are you sure they are 100% the same? You have one molecule here, and they synchronize each other, go through the cylinder the same way? No way, right? They're just random, okay? But from the global point of view, from the micro point of view, they are the same. But if you go to the single atoms, they're totally different, so random, right? They're totally different. That means for a microstate, although we cannot distinguish, but still, if you go to the micro structures, they can be very different. But all these kind of microstructure give you the same global state. Correct, everybody? So to be more precise, there's a good example on the textbook. Okay, consider we only have three molecules. We only have the three molecules. Three molecules. Okay. And then the total energy is 3. Okay, total energy is 3. Don't worry about the unit. Arbitrary unit. Okay, we have 3 molecules, 3, and the unit is 3. Okay, and we put this one in the parking garage or whatever. We have the parking garage. The parking garage have totally 4 energy levels. The first energy level have energy of 0. The second one, the first one have 1. Second 3. Okay, so if we put the molecule on the ground floor, it has no energy. Energy equal to 0. And if I put it to the first one, it's 1. Okay, second one 2. So the question is, how many different types of configuration can give you this result? Can give you 3 molecules, total energy of 3. How many different kind of configurations?
At least 3.
Huh?
At least 3.
At least 3? Yeah, more than that. What I say?
I'm asking, all the 3 molecules are 100% same or a little bit different?
That's a good question. Let's assume we can distinguish them. Let's assume we can distinguish them.
Then they're ABC, right?
Yeah, we can call them ABC, that's fine. But all of them are same type, okay? I'm human, you are human, you are human, you are human, but we look different, okay? Now, anyway. But if you bring another kind of animal, we just increase the entropy, of course. Anyway, so how many different configurations? We put 3 molecules into this system, and the total energy is 3. How many different kind of the configurations?
3 factorial is 4.
Huh? What's that?
6.
6? Let's try, okay?
More than that.
Well,
Because there is another space.
Okay, we need to let me make the definition more clear. First of all, we talk about configuration. Right now, you know the microstate, right? In this one, the microstate means we have total energy of 3. That's it. This one is the microstate, okay? This one is the microstate. Okay? The microstate is what? Is the energy. Okay? And the configuration. Configuration means how many molecules on each of this level. Okay? How many molecules on each of this level. That's the configuration. Okay? For example, like you go to parking garage, you do not know on this spot is Toyota, on that spot is Honda, on that one is the Ram, on that one is whatever. You don't know, you don't worry about that. You just only told me how many cars on the first floor, how many cars on the second floor, how many cars on the third floor. We do not distinguish them first. Okay? So that one is configuration. How many different types of configuration can possibly achieve by this?
12. 12.
12? Which 12? I mean,
0 can be filled in 3 ways. 1 can be filled another 3 ways. Like that.
but the total energy needs to be conserved.
Oh, okay.
You can have 1 on 3 and 2 on 0.
1 on 3. Okay, let me see.
Conform to that.
1 on 3. 2 on 0.
Oh, okay.
Right? 3, 2, 1, 0. This is the one configuration. What something else?
You can have
With that same
Cool.
one,
You
you
could
could
have
have
that
two
two more
molecules too.
times.
What's that?
You could have that 2 more times, and then you could have 1.
No. I mean the thing. Which one? Two more times.
Cycling between the molecules, which one?
No. Right now, this is not configuration anymore. And
Okay.
configuration only means how many molecules on each level. We do not distinguish them now. Okay. Right now, we do not distinguish. As I mentioned, I don't care whether it's Toyota, Honda, or like Ram or whatever. Doesn't matter. 2 cars on first floor, 1 car on third floor. That's it. Some other configurations.
2 plus 1 plus 0.
2 plus 1 plus 0. 1. Okay. Something else?
1, 2, 3.
Huh? What's that?
1 and 2 and 3.
1 and 2 and 3. If you have 1 and 2 and 1, 3, total energy is 6.
This 2.
3 on 1.
1, 1, 1.
1 on 2.
1, 1, 1.
1. Something else? That's it, okay? So this is what we call it configuration. That means how many atoms from the level. Right now we do not distinguish them yet. Okay, let's further go further down. Microstate, okay? Microstate. How many different states we can have in this configuration? Right now we consider the molecules are distinguishable. We have 3, right?
3 factorial.
We have 3. So this one can be particle A, particle B, particle C. Right? And then the rest on the first floor. What about this one? How many different configurations for the how many different kind of
If
microstate?
you consider these 3 as different,
Yeah.
you can do it in 3 factorial ways.
Yeah, that is what? What's the number?
The first
6.
one, I'm talking about the first column.
Yeah, what
That
first
can
one?
be done 3 factorial ways.
Yeah, don't worry about the 3, right? The final result is 3, right?
No, 6.
Which one is 6? This one is 6? Why do you think it's 6?
Yeah, 2, 6, 'cause that could be a
If
factorial
you
of 3.
exchange,
Yeah, if you exchange, but the thing is like you have A and B and C. And the B and C are both frequent the same result,
oh,
right? The same configuration. What about this one? 3? All the different 3 configurations? Think about it. A, B, C. A, C, B. Right? And we'll put the B here. B, A, C. B, C, A.
6 ways.
6. How do we calculate it?
3
3
factorial.
factorial.
Right? So you can, yeah, something like this. Okay, but we know as this. What about this one?
1.
Okay. So right now we have 3 for the same microstate. We have 3 configurations, and for each of them we have several microstates. Right now, ask me a question. So which configuration has the highest possibility? This one, right? This one has the highest possibility. So that means if we come here to see the garage, we have a higher possibility to observe this configuration than this one, What's the reason for that? Because this one has the most number of microstates. Correct, everybody? Okay. Right now we get the key point. The key point of the static thermodynamic is each of this kind of microstate has the same possibility, statistical possibility. Okay? We have the same possibility. Okay? And then because they have the same possibility, then because each configuration has different number of microstates, then the configuration has the most number of the microstates has the highest possibility to be observed. Got the point? That's it. If you know this kind of principle, basically that's all the foundation of the statistics. Okay? I give you some time to think about it. I give you about 1 minute to think about it. And then I make the problem more complicated.
Can I make the statement again, please?
Huh?
The statement, you can repeat again, please?
No.
No.
I'm going to repeat again with another. Except him. Everybody agree for me to move on? So you can see that right now I'm still using the parking garage model to describe the distribution, the microstate. But all this kind of configuration and microstate give exactly the same macrostate, correct? Yeah. I mean, if you only care about energy, all this kind of configuration, all this kind of microstate give us exactly the same thing. We cannot distinguish them from the global point of view. Okay? All right. So the question is, this model is still simple. It's so simple. Okay? If we want to analyze the behavior, for example, like the ideal gas, how can we build up how can we project, or how can we build up a garage, represent an ideal gas system? Okay? How can we mimic the ideal gas, the tank of ideal gas, with the parking garage? How can we do the job? We know that. We know the parking garage, right? We have the different parking garage levels, right? But for the, we know that this have different energy, right? They have different energy. Energy 0, energy 1, energy 2, energy 3. But probably we even have a higher energy, energy I, or whatever. Right? This is the parking garage. Right? Different, the parking level give you different energy. And of course, the sigma, and for each of the energy, for each of this level, we have totally, we have a number of N0, N1, N3, N3, N2, N3, and Ni particles. Right? That's the distribution. Right? We do not care about which particle on it. We just calculate how many particles, right? And when we have that information, we can already calculate the total energy, right? Ni EI equals what? Equals to the total internal energy, correct? Is that correct, everybody? And then if I sum over all the Ni, we get the total number of particles, right? That's it. Remember, we have 3 particles and total energy 3. Now here the same thing. We have total number of N particles and total energy of U. Okay, we just add more levels, right? But how can this kind of behavior, how this kind of picture be used to describe the ideal gas? First of all, we need to know what is the energy of the ideal gas. So what's the particle energy inside the ideal gas? Kinetic energy. Something else? No. That's the definition of ideal gas. Ideal gas only have the motion. They do not have the interaction. Okay? We have the ideal gas moving that way. We have one molecule move on to this way. We have some molecule move to this way. So what's the energy it has? It has something like this, right?
And this,
Correct? That's the energy. We can change the way. We can also change the intensity, something like this, right? I will explain to you why we prefer to use momentum instead of the velocity to describe the energy. I will talk about at the very late of the class. But right now we know these two equations are equivalent, right? They are the same thing. Okay? Half mv squared equals to the 1 divided by, equals to the p squared divided by 2m. They are the same thing. But we have p equals to mv. Right? That's momentum. Okay, so, but you know that the energy is only a single label, right? But if it seems like a little bit different, but we still can do something like this. So instead of you talking to separate the system according to the energy, we can also separate the system according to the momentum, right? According to the momentum, that's the same thing because the energy equals to this one, right? Understand what I'm saying? So then we can reconstruct this kind of the, not necessary, I mean, this one. We just rewrite this one. Right? And then we can, yeah, we need to, let me think whether that's a proper way for me to introduce the concept. That's fine. Oh, we know that this one is related to the energy, right? So we make some small trick, okay? Instead of label them with the energy, we can label them with P. Right? The dP is the small change of the P. Right? Because I'm thinking about the gas, they are continuously distributed, right? But we just artificially define a small, give them a small gap to make them distinguishable. Digitize them. Okay? Although in the system they are continuous, but we just give a small gap for each of the change. All right, everybody? So, but this is only one dimension, but right now we are considering three-dimensional. Then the gap between each of this level actually is what? The gap between each of the level actually is the dpx, dpy times dpz, right? We give it, right now we only consider this, I mean, if we will consider dp, that is one dimension, but right now we have three dimensions. Then the gap between two neighboring level, dpx times dpy times dpz, okay? We need to consider the distribution of three dimensions. Huh? It's a volume, it's a volume. Is based on volume. This is only one dimension, right? I mean, you also need to consider other dimensions.
but if we consider the vector, why should we multiply?
That's a good question. That's very deep. I mean, unfortunately, if you reach that point, unfortunately, we need to talk about something about, I don't want to go too much about this topic, okay? So if you want to understand about why we define it that way, do you know that we are talking, this one we are talking about what? Actually, what we are talking about now, if you go through the formal statistics thermodynamics, right now we're talking, you can check online, if you feel interested, you can check online, okay? We call this kind of theory called the canonical theory. Okay? Micro means we are talking about some very tiny small system. Okay, this one is not matter. Canonical. What does canonical mean? Have you ever heard about the word canonical? What's the meaning of canonical? Classic. Something like that.
Like part of the story.
Huh?
Like part of the story.
Exactly. So, but if you go to like this kind of dynamics, any kind of dynamic system, electrodynamic system, thermodynamic, if we talk about canonical system, that means we use P and X as we call it conjugate coordinate, okay? And then we know the three-dimensional system, right? What's the small volume in the three dimension? It's a dx, dy, dz, right? But when we describe the motion of the particle, we also, this one only tells you the position. And then we have a distribution of the gas is distributed in the momentum space, something like this. So that is, we call it the monodic or independent, right? So if I want to make sure, if I want to make this more straightforward, something like this, it's something like this. So we know that we have the gas, right? And in a small volume in a space, the number of gas is what? Is the density of gas times dx, dy, dz. Correct? This is the how many particles inside this kind of volume, right? But right now we are talking about energy. Then this is x, this is y, this is z. Then you can see that in this kind of box, you have every different kind of velocity or momentum, right? Then the gas also distributed along this kind of momentum space. Right? It's become one space. And each of the points, as you mentioned, is a vector. Right? This is a vector. And if we know the vector or the coordinate, we know the speed of the single molecule. Right? And then we can see that if we go to this space, the molecule also have some distribution in this space. It's distributed everywhere. In the momentum space or in the energy space. Correct? Some one have higher energy, that means point from here. Some particle have very low energy, simply doesn't move. If it doesn't move, the particle is here. Right? So how can we calculate how many particles in each of this small area? The same thing is rho d, but it's not dx, y, z, it's dpx, dpy, dpz. Correct, everybody? But again, this is not related to the position. This is related to the energy. Right? That's the reason for the energy gap we use this kind of as a label. It's a volume. It's a small volume. Okay? Because we want to see how many particles in this small distribution, how many particles distribute in this small area. Okay? And this coordinate is just the Cartesian reference frame, right? It's x1, this is space. But for this one, it's called momentum space. Okay? You know what I'm saying? But we're going to touch this topic again if you want, but this is very tedious work. We probably spend about 1 or 2 weeks to go through the entire process. I don't want to do that. It's so far beyond the topic we want to talk. Okay? But anyway, so I think we have no time. But anyway, thank you so much. The reason is I don't need to prepare for the class next time. Let's see if we go to this topic. So let me check. Give me a second. So you can feel free to go, but I can show you if you want to know more about it, where you want to find the document.
Did you get that information theory piece from Veritasium?
Hmm?
The YouTube physics guy?
This guy?
Veritasium?
I don't know. I see quite a lot of YouTube video, but I don't remember names.
He did a video on that, the entropy and equilibrium.
Oh, really?
Yeah, it's a cool one.
Okay. So to answer your question, there's a theorem talk about this one. I just do not remember the English name of it. This is called the Liouville theorem, talking about the question you mentioned. It's not random design, it's not random. But for you, just remember the gap between them. Just
Yeah.
I was wondering this the other day. Like, you have u equals something like this.
you're wrong. It's positive and negative there.
So we can have negative temperature where u increase, the fixed term u increase as decrease.
Yeah,
So
yeah.
we have a negative pressure where we fix the temperature.